Hi guys, welcome to Chemistry 1001. We're talking about thermochemistry and thermodynamics. This particular topic is bond dissociation energies. They're really useful quantities for calculating heats of reactions. That is, whether things are exothermic or endothermic. And all you need to know to do this is a table of energies for how much it takes to break a particular chemical bond. Let's have a look and see how that works. Okay, empirically it's been noticed that the energy of a particular bond in two molecules is roughly the same. What do I mean by that? Let's consider methane, CH4, and ethane, CH3, and let's look at the CH bond in both of these molecules. It turns out that they're very, very similar in energy. In fact, that's why we think of a CH bond as a thing. If CH wasn't so similar, we wouldn't call it a CH bond. But it goes further than that. Consider ethene, CH2 with a CC double bond. If we break that double bond in that molecule, separate it into two CH2 molecules, and suppose we consider another molecule, CH2, CH2, CH3, and breaking that double bond, those two double bonds are quite similar. And it goes on like that. There are tables of bond dissociation energies which have been constructed, averaged over many molecules, and these can be used to calculate delta H values. So let's have a look at a few of these things. Here's the table, separated into single bonds and multiple bonds, and the units of all of this are kilojoules per mole. Let's look at the single bonds first for carbon. So here we have the CH bond, 413 kilojoules per mole. That doesn't mean it's exactly 413 kilojoules per mole all the time in all the molecules. It's an average of the CH bond energy over different molecules. And here we have different energies calculated for a CC single bond, CN, and so on. It's kind of interesting, isn't it, that the CH bond is so energetic. It's 413 kilojoules to separate that proton from the carbon. That's a lot. Most of these are a bit less. Carbon fluorine is a bit stronger. You might have expected that at 485 because fluorine is quite an electronegative element, so it's going to be quite tightly bound to the carbon. But maybe you wouldn't have expected that for the hydrogen. It does actually make sense. The hydrogen is just a proton, and protons don't have any electrons around them except for the one electron, so it's attracted very strongly to the electrons in the chemical bond. Compared to the CC single bond, that's actually got the carbon atoms have got a cloud of electrons around them, and those electrons repel each other, so that leads to a lowering of the CC bond energy. Of course, the nucleus inside the electrons is attracted to all the electrons, but the electrons around each carbon atom are a bit repulsive. Okay, so that's a CH single bond, and you can see all the other single bond energies here, pretty much in the range 480 and as low as 150 for II, but some of the chemical bonds are really, really weak. Hydrogen bond energies are very weak, for instance. Let's look at a CC double bond. That's 614 kilojoules per mole. Is it double a CC single bond? No, not quite. It would be about 700. It says 600, a bit less than double. But it's close. CC triple bond, it's not 3 times the CC single bond, and it's not 50% more than the CC double bond. So yeah, they are certainly stronger, CC triple bonds, but they're not 3 times stronger. So there you go. Let's take a bit of a time out here and look and see at the bond lengths that go with these typical bonds. Here are the single bonds, double bonds, and triple bonds for carbon, and you can see they form a decreasing sequence: 1.54, 1.34 for the double, 1.2 for the triple. So the more bonds we have between atoms, the shorter the bond length. In fact, that's one way we use to classify single, double, and triple bonds. But we also know now that as the bond length gets shorter, the bond dissociation energy gets larger. the energy required to split the bond up gets larger as the bond length gets shorter. Makes sense, doesn't it? The more tightly held the atoms are, the harder it is, the closer they are together, and the harder it is to pull them apart. Let's see how we can use the bond enthalpies to calculate delta H for a reaction. The idea is very simple. What we assume is some reactants and products, and we imagine that we blow the reactants up into constituent atoms. What that means is we break up all the reactants into separate atoms by breaking their bonds. We can calculate that by summing up all the bond dissociation energies for the reactants. And then we calculate how much energy we would get back. We would get back by forming the products, by forming all the different chemical bonds in the products. That's why there's a minus sign here. The first term is the energy to break up the quantities, positive energy, and the second term is negative, how much energy we get back to form the products. This is a bit different to the normal formula that you're used to. Normally, delta H is enthalpy of the products minus the reactants. This is the opposite way around. If this is a bit confusing, look at this diagram here. Here are the reactants, here are the products, red and green. The sum of the bond energies raises the system into separate atoms, hypothetically, and then these atoms re-react to form the products, and we get back the energy from the negative, the bond dissociation energy. That's the bond formation energy. The opposite of the bond dissociation energy is the bond formation energy. It's negative. We get energy back. That's the idea. Shall we have a look and see at a particular example? It's always a good way, isn't it? Here's the combustion of CH4 with oxygen to form, of course, carbon dioxide and water liquid. So the system has cooled down and the water gas has condensed to water liquid. How would we calculate delta H for this reaction using only bond dissociation energies? It's easy. We have to break up 4 CH4 bonds in here, and we have to break up 2 O2 double bonds. That gives us quite a large amount of energy, which is calculate here. 4 bond dissociation energies for CH and 2 bond dissociation energies for O2. And here is the result down here. Likewise, we calculate the bond formation energies for forming 2 CO double bonds. CO2 has 2 CO double bonds. Let's go down here and look at the Lewis structure in case you don't remember that. C double bond O, C double, we form those 2 bonds instead of breaking them, so that gives us negative 2 times the bond dissociation energy for C double O. That's 1598 kilojoules per mole. And likewise, we form 4 OH bonds in these 2 water molecules, and here are the 2 water molecules here, 1, 2, 3, 4. Total negative 3466. Add that to the bond breaking energy 2648, and we get a net of minus 818 kilojoules per mole. That is the approximate delta H for that reaction. It's probably accurate within about 2%. Quite good. It's not the exact energy because these bond dissociation energies are not exact but averages over different molecules. That's how it works, guys. Now you can try yourself.